Here's something. Hey, thank you.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Awesome. All right, so today we are moving on to the next topic. So last time we finished up our discussion of 1D finite difference problems in diffusion. So today we're moving on to the next main, I would say, behavior of Navier-Stokes, which is the phenomena of convection. So it's the same idea. So we're going to be applying finite differences to these types of problems. But what you're going to see is that because convection just fundamentally is a very different type of transport than diffusion, we have to kind of treat it differently in the numerics too. So it's very interesting kind of to see kind of the marriage of physical interpretation and just how we approximate how we compute it in the computer, right? Yeah, so I think that's all my announcements. So we are moving pretty quickly. Hopefully everyone had a chance to finish or submit the poll for for their computing preference. So I took a look on Monday. I haven't had a chance to check the last couple of days, but just everyone just make sure that you fill that out just so I have a good idea in terms of what everyone's computer situation is like. So as I'm crafting kind of the tutorials for OpenFOAM and for Linux and everything, I kind of better know where everyone stands. Okay. So remember there are points associated with it. So you get 10 homework points just for filling it out. It's literally just one question. So I think the average time to complete it on the Canvas site is like 8 seconds. And so it's like 8 seconds for 10 points. So pretty good. And then the other assignment that's out there is homework 1. So homework 1 is due next Wednesday. So you have everything that you need to do homework 1. We finish all the content for homework 1 on Monday. So you can expect homework 2 to be posted, right when homework 1 ends. So Wednesday next. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go and get started. All right. So topic today is convection with finite differences. All right. So kind of the way that the early part of this class is structured is, we're taking, ultimately our goal is to be able to find numerical solutions to the Navier-Stokes equations. Of course, the problem with that is that Navier-Stokes is a really hard equation to solve. And so the way that we're kind of approaching it is we're kind of learning how to approximate, learning how to compute each individual component of Navier-Stokes, and then eventually we're going to bring it all together. Okay. So let me write out the Navier-Stokes equations one more time here, just so that you can kind of see what they look like. Right. So this is the 2D Navier-Stokes equations. And again, our emphasis is on the momentum term of Navier-Stokes, just because that's the term that's more I would say iconic to Navier-Stokes. So the continuity equation, and we'll get to the continuity equation once we get to pressure volume coupling. We'll probably get to that kind of right before the spring break, but we're focusing just on the momentum equation. Okay. All right. So far, for the last couple lectures, we've been focusing mostly on this term, right? So this is our diffusion term. Okay. So we'll talk today a little bit about why we call that the diffusion term and what that kind of physically represents. Okay. And I guess technically you could also say that we've included the source term as well. Remember, the source term is just any kind of external forcing or external function that's going to be affecting our solution. Anything that does not include the velocity section. Okay. All right, so we know how to do these ones. So remember, diffusion essentially is just a second order derivative. Source term is just any kind of function that doesn't depend on our dependent variable. Okay. Okay, so today we are going to be bringing in, I would say, the next big component of Navier-Stokes, which are these terms right here. Okay. So we call these the convection terms. Or, if you want to be kind of pedantic, technically these are the advection terms. Okay. Right. There is a difference between convection and advection if you're being very pedantic, but they're essentially kind of the same thing. And so what you're going to see is that, these terms here, essentially they are first order derivative terms. And then they're going to bring their own challenges to clear. Okay. And then the other two terms that we have left there, the unsteady term and the pressure term, we'll deal with those, as the semester goes. But, I want to just kind of focus on these ones first. Okay, so let's talk about convection first. Okay. Let's talk about what convection actually is. Okay. So if you've taken heat transfer, the idea of convection should hopefully be very familiar with you. So convection is the active transport of some species or some quantity via a moving fluid. Okay. So I think most people are introduced to the idea of convection, when you first take a heat transfer class. And so heat transfer, you learn that convection is the active transport of thermal energy or heat via moving. Okay, so I say substance here. Maybe just substance is not the right word for it, but it's the active transport of some kind of quantity. Okay. So for example, let's say that you have a fan. Right? And this fan is rotating. And so it's creating a stream of air this way. Okay. And then let's say that you have a canister of an air freshener, right? And you spray that air freshener into the stream of the fan, right? What do we expect to happen? We expect that the particles from the air freshener are going to travel along the paths of the airflow to go from the left to the right. Okay. All right, and of course you can think of many other examples of convection transfer. Okay, so I think this was just kind of a very straightforward. Okay. All right. So what are some characteristics of this kind of phenomenon here, right? So first thing that we should note is that there is a very inherent sense of directionality to this idea, right? So when you have convection, the whatever species that you're transporting, whatever quantity you're transporting, is always going to go along with the flow, right? Okay. Which of course, is semi-obvious, right? So you spray air freshener into a fan, you don't expect the air freshener to go perpendicular to the flow, or back up the flow, right? You expect it to go with the flow. But this idea actually is going to manifest itself, very interestingly when we choose our finite difference loop. So, that's kind of one thing that I want you guys to keep in mind. Okay? Now, when you're talking about convection in Navier-Stokes, Navier-Stokes is very unique because, in Navier-Stokes, what we're actually transporting here is not necessarily a species of some kind, but we're actually transporting fluid momentum, which is, remember, like we said, those convection terms are inherently nonlinear, because we're saying that the fluid velocity is kind of transporting its own momentum, so it's kind of like a nonlinear kind of self thing. So we'll deal with that nonlinearity later on in the class, but for now just think of convection as kind of just an active transport in one direction. All right. Any questions on this so far? Okay, so let's contrast convection with the phenomenon that we've already covered, which is diffusion. All right, so diffusion is another mode of transport that can occur in a fluid or whatever. Okay, but unlike convection, where convection is an active transport, we usually say diffusion is passive transport. And so we said that diffusion is the passive transport of a substance via dispersion. And what's unique about diffusion is that it occurs equally in all directions, right? So we usually say diffusion is kind of like passive spread. Okay? So diffusion is something that we generally expect to happen in most situations, right? So, let's take an example where, let's say that we have a glass of water, right? Okay. And then let's say into this glass of water, we're going to drop a little, a little drop of some kind of food dye. I've been hearing a lot of buzz on social media about red 40. So you can imagine this is red 40. Apparently it's really bad. But, uh, okay. So what do we expect to happen if we were to drop, a very concentrated droplet of food dye into this glass of water and we just left it alone, right? Eventually, what we expect is that that food dye is going to spread out, to the rest of the container, right? That was terrible. I thought that was going to come out lighter, right? So when things spread out, generally what you expect is that, first of all, it's kind of domain of reach expands, right? So it spreads out, but also it gets kind of less and less concentrated. So you see it, not as bright. It kind of, becomes more dull, right? Okay. So of course, the key here is that diffusion occurs in all directions. Because if you're passively spreading, you don't really get to choose, what direction that you get to passively spread to. You just kind of just let it happen. Right? Okay. So, all the problems that we've seen so far, we've kind of, we've been doing diffusion, even if we haven't explicitly done. Right? Now, with this in mind, let's look and see how we typically treat the diffusion term with finite differences, and let's see how if that's consistent with its physics, with what we expect. Okay? Okay. So remember, the diffusion term is always going to be a second order derivative. So we have d squared phi dx squared. Okay. Right. And then in our approximation, we use a second order central differencing scheme to represent our second order derivative, right? And so we said this is phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta x squared. So remember, we called it a central scheme because it's a scheme that's centralized right on the node that we're interested in, right? So, if you look at this equation here, in order to form this finite difference approximation, we need information from the current nodes. We need information from phi I. We need information from the left neighbor, and we need information from the right neighbor as well. Okay, and all of this occurs in a very balanced form. So, if you were to draw the stencil. And let's ignore the delta x squared for a second for this scheme. Okay. Right. And so if I were to write in the coefficients for our central difference scheme, it would look something like this. So at phi I we'd have a -2, I plus 1 we'd have a 1, and then I minus 1 we'd have a 1. Okay. Right. So all I did was just, I wrote out kind of each of the neighbors and I wrote out what the coefficients are, just so that you can see that this is very balanced, right? So, we don't really prefer any particular direction. We have equal weighting on the left and equal weighting on the right. Okay. All right, and this makes sense, right? Because, if we look at the physical, interpretation of what diffusion is equal spreading in all directions. And so, it makes sense that our finite difference scheme also is not going to be, it's not going to choose a direction. It's going to go equally one direction or another. And then what you'll see, so next week we're going to start tackling 2D equations. So even in 2D, when we do the finite difference approximation for that, we're going to see that our finite difference approximation for 2D diffusion is going to go equally in all four directions. Okay? But for 1D, we can see that we're going equally to the left and to the right. Okay? All right. So, I haven't really brought up the physical intuitions up until this point really yet, just because it hasn't really been relevant. But you're going to see that, this physical understanding is going to be really important for convection and how we choose how we choose. All right. Any questions on this so far? Okay. All right. So let's look at the finite difference approximation for the convection term. Okay. Okay. So convection, let me go ahead and write out the term for that. Convection is the following. So you have u d phi dx. So essentially, the part we're going to focus on, of course, is going to be the derivative, right? So convection is always characterized with the first order derivative. Okay. All right. And so we know we've seen this, before, that for first order derivatives, we have several different options in terms of how we can discretize it. Okay. So let's write out all three options, and then I'm going to do the same thing I did for the diffusion term, where I'm going to write out kind of the stencil, and we're going to see how it provides weighting to each of the neighboring terms. Okay. Okay. All right. So first option, usually our first instinct to approximate first order, excuse me. Our first instinct to when we are approximating first order derivatives is to use our central difference scheme. Okay. So for a first order derivative, that is phi I plus 1 minus phi I minus 1 divided by 2 delta x. Okay. And once again, if we ignore the delta x in the bottom, we can, draw out the weights. Okay. So for a central difference scheme, we have weightings that look like this. We have a positive 1 on I plus 1, and of course, a negative 1 on I minus 1. Okay. Okay, so next one we have is the forward difference scheme. So forward difference is phi I plus 1 minus phi I divided by delta x. Okay. All right, so once again, let's go ahead and draw out our stencil. Okay. So this one, the stencil is you have a positive 1 on I plus 1 and a minus 1 on node I. Okay. So with forward differencing, we're biasing a little bit to the right, right? So, we don't require anything from the left neighbor. Okay, and then let's look at backward difference. So backward difference, we have phi minus phi minus 1 divided by delta x. Okay. Once again, let's draw our weights, I plus 1, I minus 1. And so our weights in this case, we have a positive 1 on phi and then a minus 1 on phi minus 1. Okay. So again, for backward differencing, we have a bias. It's not balanced. We place more weight on the left-hand side. Okay. And remember that forward difference and backward difference, that bias comes with a cost. And that cost means that, these schemes are only first order accurate, right? Whereas our central difference scheme, remember, we have second order accuracy. So the error term decreases as delta x squared. Okay? So we would prefer to use central differencing just because, our diffusion term is also central difference in second order accurate, right? So it'd be great if our convection term were also had the same order of accuracy. But what you're going to see is that accuracy is not always the only consideration that you have to make when you're finding numerical solutions to these types of equations. Okay, so to kind of illustrate that, I have an example, and I have a MATLAB code that goes with it. I've posted the MATLAB code. Again, it's not going to be something I'm going to expect you guys to program, but I am going to use the MATLAB code to kind of illustrate to you what happens under these kind of different schemes. Okay? But before we jump into that example, are there any questions? Okay, all right, so let's jump into an example. Okay, so for this example, we're going to have a convection diffusion problem along with the source. Okay, so we're going to solve for the solution to the following problem. So you have 3 d squared phi dx squared minus 75 d phi dx is equal to minus 8x. Okay. All right, so right away we can go ahead and identify all the terms. We have our second order derivative. So this one we can automatically see this is our diffusion term. Okay. Next, we have a negative 75 times the first order derivative of our transport quantity phi. So this means this is our convection term. Okay. And then finally, we have the minus 8x. So this is just kind of an extra term. It does not involve phi in any way. So this right here is, we usually call this like our source term. Okay. Okay. All right, so for a first, for an ordinary differential equation like this, technically we can find its solution, right? We don't need numerics, so we can actually solve this one by hand. So I'm going to skip the details for that just because it's a little bit cumbersome. It's not super cumbersome, but a little bit too cumbersome that I want to go over in the class right now. So if you were to solve this by hand, you probably need some kind of integrating factor, separation of variables kind of technique in order to do so, right? So memories of 308 and 250p. But if you were to do that, you end up with the following: p of x is equal to 589 divided by 625. Okay. Multiplied by 1 divided by e to the 25 minus 1, e to the 25x minus 1, okay, plus 4 over 75 x squared plus 8 over 1875 x. Okay. So, not the most straightforward solution, but it's there. Okay. Oh, I forgot the boundary condition. So the boundary conditions in this case, we're doing that a lot lately. I'm teaching a section of 308, and I always forget to put the boundary conditions too. So our boundary conditions in this case are pretty straightforward. So we're going to have two Dirichlet boundary conditions. So we're going to have phi of 0 is equal to 0, and then phi of 1 is equal to 1. Okay. Okay. So we have our 1D problem. We know its exact solution, right? Normally, we can stop here, but this is, we're trying to learn finite differences. So let's try to find the finite difference solution to this problem as well, or at least get an equation for the for the finite difference equation. Okay. So when we apply finite differences to this equation, we're basically going to take every single derivative and represent it and replace it with the finite difference approximation. Okay. Now, in doing so, we do have to make decisions, and so we have to choose which finite difference scheme that we actually want to use for each of these terms. Okay, so let's start with the diffusion term. So this one's straightforward. We only have one choice, right? And so we're just going to use our usual central difference scheme. I'm going to take the, just because we have the coefficient of 3 out in front, I'm just going to factor out the delta x squared from the denominator just so we can focus on the interior there. So you have 3 divided by delta x squared multiplied by phi plus 1 minus 2 phi I plus phi minus 1, okay, minus 75. Okay. Now for the convection derivative, remember we have options in terms of how we want to discretize this. We can choose central difference scheme, we can choose forward difference scheme, or backward difference. Okay. Let's try central first, just because we're allured in with the promise of second order accuracy. Okay. So we're going to factor out a 2 delta x, and this is multiplied by phi plus 1 minus phi minus 1. Okay. And this is all equal to minus 8xi. Okay. Okay, question, yes.
Sorry, can you explain again real quick why you chose that specific scheme?
The central difference?
Yeah.
Just because
the one forward.
This is central difference here. So you have I plus 1 minus I minus 1. So we chose central difference. For now, it's mostly arbitrary, but we chose it just because it's the most accurate scheme that we know. because forward difference, backward difference, we know are only first order accurate. And so, usually we want to aim for the highest accuracy. So we choose central difference. All right, any other questions on this? Okay. All right, so typically what you do from here, questions.
I don't know if this is a trivial question, but if you use a central scheme, does it have to be central for all of them?
It doesn't have to be, no. And so we can choose a mix. And so, so we can choose central difference for the second order derivative, and we can choose like forward difference or backward difference for the other two. Yeah. Now you do kind of run into the issue where, your derivatives are not going to have the same order of accuracy anymore. And so, we talked about that before, where you usually don't want to do that because, you want everything to kind of have the same order of accuracy generally. But sometimes there are other factors that are more important than accuracy that you kind of have to compromise. So you kind of have to compromise on accuracy in order to get something else from your solution. And so you're going to see that in a second. Okay. So typically, after you've plugged in your finite difference schemes, what you usually do at this point is you group the like terms. And so you can see on the left-hand side, you have multiple terms that have phi plus 1, multiple terms with phi minus 1. So let's just group them all together so we have just a fixed coefficient for each one. Okay, so let's get all the terms for phi plus 1. So for phi plus 1, we have a 3 over delta x squared. That comes from the diffusion term, and then we have minus 75 over 2 delta x. Okay. And that's all multiplied by phi plus 1. Okay. All right, and then we have the coefficient for phi. We only have one contribution to phi, so that's a minus 3 times 2 divided by delta x squared. So that's minus 6 divided by delta x squared. Phi plus. And then we have the coefficient in front of phi minus 1. So that's a 3 divided by delta x squared. That's the contribution from the diffusion term. Plus, just because we have a minus, 75 over 2 delta x. Phi. So this step is always really useful just because, eventually, if you guys have already started on the homework, eventually you're going to take these finite difference equations and these become the rows in your matrix for the, for the system that you're going to solve. And so, it's easy, it's a little bit more convenient to group the like terms just so that you can compute the coefficient very easily, right? Now, of course, these coefficients here do depend on the grid spacing. And so I haven't plugged in for delta x yet. We haven't defined a grid just yet, but as soon as you have a grid, you know how many points you're working with. You can plug in for delta x. Okay. But for now, let me go ahead and box this up. So we say this is our finite difference equation for this particular problem. All right, and of course, depending on depending on what we plug in for delta x. Okay. All right, so I'm going to go ahead and switch over to MATLAB for a second, just so you can kind of see what's going on. But just kind of keep this equation in your heads, right? And we're going to see what happens to our solution for different schemes and for different values of the grid space. Okay, so let me go ahead and switch over to MATLAB. Okay, so this code, I just posted this on Canvas, and so this code is called EGME, well, so I originally prepared this code for 417, which is another elective that I teach. Convection-Diffusion class activity, okay? So this is for the exact same equation here. In fact, I've also plotted the exact solution for you here as well, okay? Okay, so again, the details of this code, don't worry about it too much. This is, if we were going to get into the MATLAB programming, I would, have you guys learn how to do this. But for now, just don't worry about it. Okay. The point is that, we're going to solve for this solution in two different ways. So we're going to solve for this solution with central differencing, and we're going to solve for this solution with backward differencing. Okay, so let's look at central differencing first, and then just to make things illustrative, let me go ahead and change the number of grid points to 7. Okay. So if you're going to be playing with this code, at home, just know that you can change the number of grid points by changing n. Okay. So this n right here is the number of grid points. Okay, so let's go ahead and run it. Okay. Okay. So let's look at this plot right here and kind of see what's going on. So you can see there's 2 lines here. So in the red is the exact solution. So that's basically that gimungo function with 589 over 625, right? That's what the solution should be, right? And so if we do our approximation well, we do everything right, then our finite difference solution should match up with this one, ideally. Okay? But it doesn't, right? And so our finite difference solution here is in blue. And you can see it's doing this kind of weird behavior that we've never kind of seen before. We have these kind of like, we call them kind of oscillations. And so you can see that the solution kind of jumps up, then it jumps down, then it jumps up again, then it jumps down, then it jumps up here, okay? Now, it's not supposed to do that. So, typically when you're solving, numerical solutions to these, heat equations, Navier-Stokes, it's extremely unusual to observe these kinds of oscillations, just that they don't really happen in real life, except under very special circumstances. And so if you're looking at, shocks in a hypersonic aircraft engine, then yeah, you have oscillations there. But for the most part, you're not really going to be looking at those kinds of situations. And so these oscillations are extremely unusual. So we can say that they're weird. Okay. So this phenomenon here kind of brings up another aspect of numerical solutions that we haven't touched on up until this point, and that is the notion of stability. So stability is very interesting because it's not something that you generally expect to happen in a numerical solution. But if you're not careful with how you approximate your solution, how you choose your finite difference schemes, even in established software, so even in OpenFOAM, where you're not actually doing any of the programming, you can still get unstable solutions. And so stability is the sense that or stability is the phenomenon where if you don't set up your simulation correctly, you're going to get these very unnatural perturbations or unnatural kind of oscillations in your solution. Okay. So I'm not going to write that out. I'll write that out in the iPad. But okay. And so why does that occur in this case, right? So remember, for this problem, we've chosen a central differencing scheme for our convection, right? And so in this case, convection is going this way, right? And the scheme that we used, right, was equally weighted on the left and right of our neighbor. So even though I know one of the weights is negative, the other is positive, but you can just think of them in terms of its magnitude, right? So we have equal weights on the left-hand side and equal weights on the right. Okay. Now for diffusion, this worked great because diffusion, diffusion is a phenomenon that occurs equally to the left and to the right. Okay. But that's not really the case for convection. Convection has a very specific direction in which the transport is occurring. Okay? And so in some sense, it doesn't really make sense for us to have, equal weightings on both sides because, we should be weighting one side more than the other for a phenomenon that has a natural direction. Okay. Okay, so let's look at the exact same problem. And then I'm going to switch it up. And so instead of doing a forward different or a central differencing scheme for the convection, I'm going to be doing a backward differencing scheme for the convection. So exact same problem, exact same methodology. Our diffusion is actually still exactly the same. The only thing is that I'm switching from a central difference scheme for the convection to a backward differencing scheme. Okay. Same number of grid points, same problem, everything. Let's go ahead and run, and let's see what happens. Okay, so this is what our solution looks like for a backward differencing scheme. So you can see that, those unnatural oscillations or unnatural kind of jumps are gone. And so, we now have a stable solution. Okay. It's stable, but it's inaccurate. So you can see here that, we have kind of a very big difference here in terms of the solution. So, the finite difference solution should be over here, but instead it's up here. So, it's inaccurate, which is what we expect, right? Backward difference is only first order accurate, but at least we're stable. We're not getting any kind of weird jumps in or anything like that. Okay. So why is that, right? Let me go ahead and draw the direction of convection one more time. And let's draw the weightings for our backward difference again. Okay, so we have I minus 1, I plus 1. Okay. Okay, so if you look at the weightings for our backward differencing scheme, everything is kind of biased to the left here. Okay. And if you compare that to the direction of our convection velocity, right, you can see that we have more bias on the upstream side. Right, so when I say upstream is basically the direct, or is the direction where the flow is coming from, right? So in this case, flow is coming from the left to the right. And so, we should put more weight here in our scheme, okay? And that's exactly what the backward differencing scheme does. And so, because the information or because the species is, flowing from left to right, then our differencing scheme should also go in that direction as well. Okay. Okay, and so with that, you get a much more stable, if not inaccurate, solution. Okay. All right. Any questions on that? All right, so with convection, and now with this idea of stability, it's kind of another factor to consider, when you're choosing your scheme. Okay. All right, I'm going to show you one more thing before we jump back into the nodes, right? So I ran this problem with a fairly coarse grid, right? So 7 points is not all that much, right? So let's see what happens when we increase the number of grid points. Okay? So generally, when you increase the number of grid points, remember we expect the accuracy to get better, right? Right? Because even for a first order scheme, if you increase the number of grid points, you reduce the size of delta x. And by reducing delta x, you reduce the amount of error in your solution. Okay. So let me change the number of grid points from 7 to 21. Okay. Right, and you can see here that we're doing a little bit of a better job. So, as we increase the number of grid points, this solution will start to kind of match this one a bit better. Okay. We can even go further, so we can even go crazy. We can change it to 201 grid points. Okay. Right. So at 201 grid points, you can see that, we're matching these solutions much more closely. Okay. Right. But I'm going to show you something interesting. Okay. So let's go back to central differencing scheme for a second. And then let me set the number of grid points at 21 again. Let's see what happens. Okay, so this is our solution with central differencing scheme with 21 grid points, right? So you can see that when we increase the number of grid points to 21, right, we don't have those weird oscillations anymore. And so this is with central differencing, okay? In fact, our solution actually looks really good. And so our solution is hugging our exact solution very well because of that second order accuracy, right? And if we increase the grid points again, let's look at this for 201 grid points. And so with central differencing scheme and 201 grid points, the two curves are basically indistinguishable from each other. So, even though there technically still is an error term in between your finite difference solution and exact solution, it's so small that it's basically imperceptible. Okay. So that's the kind of interesting thing with stability, is that it can kind of hide from you a little bit, because if you refine your grid enough, if you increase the number of grid points enough, usually that's going to fix. Well, increase the number of grid points kind of fixes a lot of things in numerical solutions. And so if you're able to do that, then you kind of the term that we kind of use it for in in the industry is you kind of just brute force your way past the problems, right? And so if you have the computer power to do that, then by all means you can do that. It's very valid. In fact, there's a whole scheme in turbulence for this called direct numerical simulation, called DNS, where you don't do anything fancy. You just solve regular Navier-Stokes, but you make your grid so small that it's almost impossible for any kind of errors or weird stuff to happen. The only problem with this is that increasing number of grid points is not always practical. Because doing something like this for a cheap problem like this, absolutely we can even crank this up to 20,000 nodes. It'd still be fun. But for more practical problems, that's not always the case, right? And so for more practical problems where you can't just brute force your way past everything, you need to be a little bit more elegant in terms of how you do this solution. Okay, but I did want to show you that, at least, where a lot of times you can just like I said, just reduce the grid sizing enough until all your problems go away. Okay. Bring OneNote to load. There we go. Okay, so let's well, as soon as that black bar goes away, let's summarize kind of what we found from that example. Okay. All right, I guess this black bar is here to stay. Okay. So let's talk about stability first. Okay. So stability in numerical computations refers to the fact that numerical solutions under certain conditions can have unwanted and unphysical oscillations in the solution. Okay. So those oscillations are often not physical at all. So that's not something that's modeled by the underlying equations. Okay. And the scary thing about stability, you don't really see it in these kind of simple problems, but this is true once we get to kind of time marching and unsteady problems, that these oscillations can grow unbounded. And so you can actually get floating point exception errors in your computer if you kind of leave them unchecked. Okay, so the one example that we have so far of this is that, choosing a central difference scheme with a coarse grid for convection dominated problems. All right, so that's exactly kind of what we saw in the in the example that we just did. Okay. Okay. And so the reason we saw unstable oscillations in the system or in the solution here was that a central differencing scheme is not really appropriate for a physical phenomenon like convection, which has a preferred direction. And so the solution to this, we saw that there are two solutions. So the very simple solution that honestly a lot of people just go for is just the kind of the unga bunga brute force solution, which is just to refine the grid enough so that it's not a problem. But again, that might be possible for simple problems, and even for some practical problems. I mean, computing is getting more powerful every day, but that's not always going to be practically available. Okay. So how do you know, right? So if you did want to go with the Unga Bunga approach, how do you know how much do you need to refine the grid in order to make it stable? Well, in reality, there's no exact way to do it, but there is a pretty good measure for it. Right? So every numerical scheme has something called its stability criterion. So basically, some kind of non-dimensional number that you can compute to determine whether your solution is going to be stable. Okay. So once we start doing CFD, we're going to talk about something called the CFL number quite a bit. So CFL number is kind of the de facto criterion for stability for Navier-Stokes. Okay. But for a more simple kind of convection diffusion problem like this, there is a simpler metric called the Peckway number. Fun fact, there's a Hello Kitty character named Peckway. It's like a duck. My wife made me wear a Peckway shirt to our nephew's birthday party. Still have it. I tell my wife, oh, there's a non-dimensional number named after this. And she's like, shut up and put on the shirt.
You gonna wear the shirt?
Huh?
You gonna wear the shirt to class?
No, it's not professional. I wear a button up for class. Maybe on the last day. If you guys remind me in a semester, I'll wear it to class. All right, so the Peckway number is very simple. So we basically take your convection velocity u multiplied by delta x, which is the grid spacing, divided by k, which I realize we haven't used k yet, but k here, this is the diffusion constant. So the diffusion constant is just the number that's in front of the diffusion term, right? So if you go back up to our previous example, right? Where was it? Here it is, right? Oh. There it is, right? So K is this number right here. Basically, whatever coefficient is in front of the second order derivative, that is going to be your K. Okay, so you're basically taking the ratio of the velocity and the diffusion constant, and you're going to modulate it by the grid spacing. Okay, just make it non-dimensional. Okay, and the Peckley criterion basically says that if this is less than 2, okay, right, and you're using a central differencing scheme, then you're going to have a stable solution. Okay. So if you want to go this route, you really like that second order accuracy, you don't really want to let it go, but you still want to get stable solutions, then you would need to check the Peckley. Okay. All right, so the reason this isn't practical all the time is that you might have situations where you have an unsteady velocity field. So you have a velocity field that's speeding up, slowing down as a function of time, and the grid is not something that you can dynamically really change. Once the grid is set, it's pretty set. Okay, there are methods out there to kind of remesh your solution midway through, but those are usually not ideal. Okay? So you kind of want to set your grid and just use that for the whole solution. Okay. So if you go back to the previous problem and if you play around with the MATLAB code that I posted, you can I think I actually compute the Peckley number there for you. And so you can see that when the number of grid points is enough such that the Peckley number is less than 2, then you're going to get a stable solution. Okay. All right, so that's one way to solve the stability problem. Okay. The other way to solve the stability problem is to choose a numerical scheme that's more consistent with your underlying physics. And so this led us to the use of our backward difference scheme. Okay. Which, for a velocity that's going from left to right, places more emphasis on the upstream direction. Okay. Now, of course, that always brings up the question, what if your velocity is going the other way? So what if your velocity is going from right to left, right? Then the proper upwinding scheme. So these types of schemes are called upwinding schemes. The proper upwinding scheme is actually going to be forward difference. Okay? So you have to be careful if you're going to go with upwinding. Actually, let me go ahead and write that in. So this technique is called upwinding. If you're going to go with upwinding, you have to be very cognizant of the direction of the velocity, because you don't want to upwind in the wrong direction, because then that defeats the purpose of the upwind. You still get an unstable solution. Okay. Now, how do you know which direction the velocity is going? Well, you should look at the sign of the coefficient in front of the convection term. Okay. Okay, so let's go back up to the example. Right, so in this example, we have 3 d squared phi dx squared minus 75 dx dy, or d phi dx, okay? Now, in this problem, you can see that we have a negative 75, okay? But, this is actually a positive velocity, right? And so the reason for that is because I was kind of an idiot, and I put the convection term on the wrong side. Okay, so usually the convection term and the diffusion term are on opposite sides of the equations for each other. right? So actually the proper location for this velocity term is actually on the other side of this equation here. So if you were to write this in kind of more standard form, this example would be 3 d squared phi dx squared equal to 75 d phi dx minus 8x, okay? So remember that. So convection diffusion always have to be on opposite sides of the equal sign. Okay? So from here, you can see that our convection velocity, now that it's in its proper place, is positive. Okay? And so positive velocity is always going to go from left to right. And so if you had a negative velocity, and so a velocity is going from right to left, then the proper upwinding scheme is going to be a forward difference. Okay? Because that's going to put more emphasis on the right. Okay. All right, so that's upwinding. So that's the other way that you can kind of deal with these kinds of issues. Okay. Now the downside to upwinding, of course, is that we lose some accuracy, right? But of course, we've found a solution to this as well, right? And so the solution to proper upwinding to maintain your level of accuracy is to use a higher order upwinding scheme. So we're not going to do that now just because it's a little bit early. But in a few weeks when we start talking about the finite volume method, there is one method for upwinding that's very, very popular, called the quick scheme. And that's an acronym. Okay. And so I believe it stands for quadratic upwinding interpolation scheme for convective kinematics, something like that. That's why they approximate. That's why they make the acronym quick. Okay. But yeah, we're not there yet. It is a little bit complicated, and so I do want to save the discussion of quick scheme later. But I at least want to introduce the idea of upwinding to you guys so that you can kind of understand what it is, why we do it, and what the result is. Okay. Now, of course, the upside or the kind of the benefit of upwinding is that now your solution stability now the stability of your solution is independent of your grid. And so if you did have to have a situation where you have to, coarsen your grid, you can at least be assured that your solution is still going to be stable. It may not be accurate, but believe it or not, sometimes that's preferable. Sometimes you can sacrifice some accuracy, just to get a solution. So maybe you're just doing some testing. You're not ready to run your full simulation yet, and so you're just running it on a very coarse grid. And so you want to just make sure that you get something just to make sure that everything else is correct. That's very common. And that's something that we'll talk about as kind of like a practical thing when you're running CFD simulations. Okay? When you're running a typical CFD simulation, you never run your full run with all the bells and whistles from the beginning. It's always kind of a step-by-step process. So you test kind of little things by little bit. And then usually on like a third or fourth or fifth simulation, then you can kind of turn everything on and go kind of full force. Okay? So there are a lot of benefits to upwinding and even reducing some accuracy. Okay. All right. Any questions on this so far? Okay. Let me just double check that I got everything. Okay, so that's it for convection. But since we have some time, let's start our discussion on 2D finite differences. Just because I anticipate that's going to be a very long discussion next. So I do want to kind of get ahead of that right now. Okay. All right, so we're all done with the 1D stuff. So the 1D stuff is pretty much all taken care of. With the exception of the time derivative. And so, the time derivative will get its own, it'll get its own section, but the time derivative you'll see is a little bit weird if you kind of treat that bit differently. So before we get to the time derivative, let's increase the number of dimensions. Okay. Okay. So by increasing the number of dimensions, our governing equation, of course, is going to be a lot more complex as well. Okay. Just to keep things simple, let's start with just the 2D diffusion equation, and then we'll go from there. Okay, so our 2D diffusion equation, and I'm just going to keep it very simple. Let's pretend that there's no source 2. Okay. And so if we go back to our Navier-Stokes equation, I'm just going to scroll up really quickly. Right. So the way that the diffusion term is set up is that we have kind of second order derivatives in both x and y, and they're added to each other. So let's mimic that same functional form here for the finite difference here. Okay, so we'll have partial squared phi, partial x squared plus partial squared phi, partial y squared is equal to 0. Okay. So we're going to ignore literally every other term in the equation except for the diffusion. Okay. So what you're going to see is that, the approach that we're going to take for 2D problems is not really all that different. The challenge in doing 2D problems, believe it or not, is in the bookkeeping. So, and so keeping organized, keeping the notation organized, keeping your grid organized. It's honestly just a lot of just staying organized with everything. That's the hard part with 2D. And I think that kind of trips people up just because I think people don't expect that to be the main challenge. Okay. Okay, so let's start with the first thing. So let's we need to make sure we have proper notation for these systems. Okay. Okay. And so since we're now in 2 dimensions, we need to have 2 different coordinates. And so we can't just use a single index I to indicate, our neighbors, right? And so if I were to draw the stencil for this part, right? And so let's say we're going to discretize this equation around some central point. Okay? And so let's say that central point has indices I and j. Okay, so that's our center. Okay. We can define our right and left neighbors the same way as before by doing I plus 1, I minus 1. Okay. So this is going to be I plus 1, comma j. And then I minus 1, comma j. Okay. And then the top and bottom neighbors are going to be, increases and decreases in the j index. So our bottom neighbor is going to be I, comma j minus 1. And our top neighbor is going to be I, comma j plus 1. All right, so with that in mind, so now that we have that notation, let's go ahead and apply our finite differences. So we have 2 second order derivatives here. So of course, we're going to apply our second order, derivative central differencing scheme. Okay. Okay. So we have, let's do the x derivative first. So that's going to be phi I plus 1, comma j, minus 2, phi I, comma j, plus phi I, comma j minus 1. Or excuse me, I minus 1, comma j. And that's all divided by delta x squared. Okay. So this right here, this was our partial squared phi partial x squared. Right, and then we're going to have our y derivative. So that's going to be phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1 all divided by delta y squared. Okay. Okay. All right, and so one thing that you should see here too is that, for the first time, we're introducing two different grid spacings here, okay? So technically speaking, you can have different grid spacings in the X direction and the Y direction. So if for some reason you want to have, more spacing in the X direction or more spacing in the Y direction, you can do that. But typically to keep things simple, we typically use just a square grid. So typically we assume that the spacing in the X and Y direction are the same. Okay. And so if we do that, so if we assume the grid spacing is the same, and what you'll see me use sometimes is that instead of just delta X, delta Y, we're just going to use the generic delta. Okay. Okay. What we can do from there is we can just factor that out. So we have 1 divided by delta squared. Okay. And then we have all the terms on the inside. So just like we did in the previous example, let's take any like terms, and then let's just combine them together. Okay. Now, unfortunately, we only have 2 like terms here. So, in both expressions, we have a -2 phi I, comma j. All the other terms are unique. And so if we put that in, we have phi I plus 1, comma j, plus phi I minus 1, comma j, plus phi I j plus 1, plus phi I j minus 1, minus 4, phi I, comma j. All right, so that's now our kind of our very simple diffusion, finite difference expression. Okay. Now, of course, the thing you have to be careful with here is the notation, and you could see me. I've already kind of messed up a couple times, and so when you're writing so many i's and j's and +1, -1, it's very easy to kind of miss one and kind of put one in the wrong place. So, you have to be very meticulous and kind of very careful here. And make sure you kind of put everything as they are. Okay. Okay. The other thing that's very difficult about 2D problems is how we're going to number our grid. Okay. So previously in 1D it was very straightforward, just because in 1D you can only really just have a line like this, right? And then usually we number the grid points kind of sequentially. So we start with, probably 0 on the left, and we count up 0, 1, 2, 3, 4, 5, 6. Right. So this was nice because, our left neighbor was always I minus 1, and our right neighbor was always I plus 1, right? So all we had to do was just take our current number, and just our neighbor was, +1, -1 for that. Okay. So in this case, neighbors, easy to determine. Unfortunately, that's not always the case in 2D. And so in 2D, there are some neighbors that are going to be obvious, but there are some neighbors that are, that can change, right? So I'm going to give you 2 examples very quick before we leave, just kind of illustrate that to you. Okay, so let's say we have a typical 2D domain like this. Okay. So typically, the way that these are numbered, and this is not a hard rule. This is kind of just preference, right? So usually you start in the lower left-hand corner, and you start labeling the nodes going from left to right. Okay, and then when you run out to the end of the row, you go to the next row. Okay, just like that. Okay. All right, so let's look at a random node here, right? So let's look at node 5, right? So for node 5, our left and right neighbors are pretty straightforward, right? We take 5 minus 1, 5 plus 1. our top neighbor and bottom neighbor, right? Right, we can see from this image, it's going to be +4 for the top neighbor, -4 for the bottom neighbor, right? But what if you had a grid which had a few more grid points to it? Right, so let's say we had a grid like this. Right, so if we look at node number 8, right? Left and right neighbor is very easy. We just take 8 + 1, 8 - 1. But our bottom neighbor is now 2, and so that's -6, right? And then you can kind of guess that the top neighbor here is going to be 14. Okay. Right. So the issue with 2D problems is that you need a more organized and kind of systematic way to kind of keep track of the node numbers and to have it and to kind of easily kind of refer to them as you're doing calculations. Okay. So when we come back on Monday, we'll talk about what a scheme like that would look like, how we can kind of make it into a very kind of simple equation, and how that factors into our finite difference equations. Okay. All right. So thank you guys for coming today. Hope you guys have a good rest of your day. Hope you guys have a good weekend, and I will see you on Monday.
Thank you.
Let's start off. I just want to know what you're looking for at the end. Like, we're looking for the value.
Yes.
More importantly, the equations.
Yep. Both. I mean, both. I mean, they're both are the equations. Yeah. Yeah. So the equations are more or less.
Yeah, it's just get all their numbers.
Yeah. Yeah. So I mean, I'll look at the first few equations and then.
Okay.
Well, only when you heard them.
Learning.
I don't know, it's just here, but.
I'm not